Hello, this is Dr. Gardner. Today we're talking about calculations that involve solutions, but we've already covered how to calculate molarities and prepare a solution of a certain molarity. So in this discussion in part 2, we're going to be looking at how to look at diluting solutions to reduce the concentration of solutes and the types of calculations that can be involved with that type of process. Now I am assuming that you've already watched my previous tutorial, part 1, on calculating molarity, and that you understand the definition of solutes, solvents, and solutions, and that you also understand what molarity is with respect to the moles of solute per liter of solution, and that you understand how to calculate molarities as you're preparing those solutions. I also am assuming that you understand how to use volumetric flasks and how to prepare solutions in the laboratory based on our previous tutorial. In this tutorial, we'll be looking at how to recognize unsaturated, saturated, and supersaturated solutions, and we'll define what those mean. We'll also be looking at an introduction to a few other types of concentration terms. Now, I want you to be aware of the other terms that we use for concentrations and the other units, but we are still focusing on molarity for the calculations for today's lecture. We'll also define what dilution is and how that relates to decreasing your solute concentration in your solutions. We'll perform some dilution calculations that will involve an equation that has the form with initial molarity, initial volume, final molarity, and final volume, or M1V1 equals M2V2. Now, sometimes the molarities will just be listed as concentrations, C1V1 equals C2V2, so you might see this form of the equation as well, even though today I'll be working with the first equation that I've given you. Okay, so let's go ahead and start looking at different types of solutions. If we consider an unsaturated solution actually has less solute than can dissolve in the solvent at that set of temperature and pressure conditions. Now that means that the rate of dissolution, which is how much the solute is dissolving in solution, is greater than any crystallization rates, which would cause precipitation of the solute from solution to form a solid. So basically what we're saying is all of the solute is dissolved in an unsaturated solution. And in fact, we could still potentially dissolve more solute in an unsaturated solution because we are not at what we call the saturation point. The saturation point of a solution is when no more solute can dissolve at that temperature and pressure without having some precipitation occurring to balance out any more solute that might dissolve. So if we define what a saturated solution is, would be a solution where the rate of any solute dissolving in a dissolution process would be the same rate as crystallization of a precipitate out of solution to form a solid. So we don't expect a saturated solution to dissolve any more bulk solute without having the same amount come back out of solution. So in some cases we're right at the saturation point, and you may not notice that you have any indicators that you're at saturation, but if I try to dissolve any more solute, we'd notice that it will not dissolve, or we'll end up with a bulk amount of solute that still does not end up dissolving in solution. Any that does dissolve will have the same amount coming back out at that temperature and pressure unless we change temperature and pressure. So I can always try to dissolve a little more solute. If I'm not seeing it dissolve, that indicates I have a saturated solution. If I already have precipitate at the bottom of my solution, that would indicate that the solution was already saturated and there was already an excess of solute that was not present in the solution itself. Now, sometimes we can take a saturated solution that has extra solute that hasn't dissolved, and we can often change your temperature and pressures to try to become more saturated and form what we call a supersaturated solution. Now, if we would like to dissolve more solute, a lot of times ionic compounds will dissolve in greater quantities if we increase temperature. Many ionic compounds can dissolve in larger quantities as the temperature of the solution increases. Not 100% of them, but quite a few. Now, gases, however, tend to become less soluble at higher temperatures. However, we can increase the pressure of the gas over the solution, and increasing pressure could increase how much of the gas as a solute could dissolve. In fact, you see that with soda pop. If you put it in a pressurized can, well, that pressure of the gas over the solution can cause the solution to become supersaturated. If you open up the soda pop can, that supersaturated solution is unstable. We will often have the carbon dioxide escape, and so you can hear that hiss as the CO2 escapes. You can see bubbles of CO2 escaping from solution. So to prepare a supersaturated solution, I might pressurize a gas over the solution to dissolve more gas, or I might increase the temperature for ionic compounds usually. As I increase that temperature, I could allow more of the solute to dissolve in that solution at that new temperature. And if I very slowly cool the solution back down, let's say to room temperature again, we can often keep that excess amount of solute still dissolved, even though we're beyond the saturation point. Now, this would be prepare what we call a supersaturated solution. That means there's more solute than should be stable at that set of temperature and pressures. And at some point, we're going to have the solute come out of solution, that excess solute, so that we end up going from supersaturated to only a saturated solution. Now, that may occur due to a mechanical disturbance. If I take a liquid-based solution and shake it a little bit, often that's enough mechanical disturbance that we initiate crystallization of the solute. It will come out of solution with the excess, and we end up with a saturated solution with excess solute present in the bottom of the flask or the container. In other cases, we could add what we call a seed crystal. The seed crystal will provide what we call a nucleation site. Now, nucleation is the process where a solute that is in solution will start to form a crystalline lattice to come out as a solid material out of solution. And in that case, that nucleation can be initiated by adding what we call a seed crystal. The seed crystal provides a nucleation site, a site where we could have more solute organize itself to form an extended crystalline lattice as solute comes out of solution. So if I add a seed crystal to a supersaturated solution, you often will see the excess unstable solute come out of solution. If you add it to a saturated solution, your seed crystal usually will not dissolve. If I add a seed crystal to an unsaturated solution, more solute could dissolve, so the seed crystal will just dissolve. So that's a good method to test for these three types of solutions. So let's consider trying to classify a few solutions when we look at them, as well as using a little more solute. We're going to call that seed crystals to see what might occur. So here I have a flask. The solution in it is clear and colorless. I don't see any solute in the bottom of the solution. So this is either probably a supersaturated solution, or it could be an unsaturated solution, or it could be a saturated solution right at the saturation point, so I'm not seeing any excess solute. I add a seed crystal here to the solution, and I see the seed crystal dissolves. That tells me, since I can dissolve more solute, that this must have been an unsaturated solution. Okay. Now, if I look at another solution, and it appears like this, and what I actually notice at the very bottom, if I go ahead and look at the bottom of this flask carefully, we notice that there's white solute. Now, this indicates that we have a saturated solution where we have excess solute, that if any of that excess solute starts to dissolve, we must have the same amount coming back out at that temperature as a precipitate. And so I see no net change in the amount of solute that's there at the bottom of the container. It's saturated at that temperature and pressure. If I add a seed crystal to this, we don't expect the seed crystal to readily dissolve. If any of the solute from the seed crystal dissolves, that would then be balanced by extra solute coming back out of solution. So I'm going to continue to see solute present at the bottom of my container here that has not dissolved. So that indicates a saturated solution. Now, here's our next solution. Now, this one is clear, but it has kind of a yellowish orange color to it. Now, I can add a seed crystal to see what happens. When I add the seed crystal dissolves again. Now, that indicates this is an unsaturated solution. Now, I want to show you that some solutes could be clear and colorless in solution, some could be colored. I could have unsaturated solution of either type of solute potentially. Now, I can often tell qualitatively, meaning by some of my observations here visually, how concentrated my solution is if I have a colored solute. Now, as I add more of my solute that provides color to my solution, I may see a darker and darker color, indicating higher and higher concentrations, meaning I'm starting to become more saturated as I continue on, but it's still unsaturated until I reach that saturation point. So realize even colored solutions can be unsaturated until I reach the saturation point, so be careful. Here again, we have another unsaturated solution. Now, in this case, I have a flask that has a clear and colorless solution in it. I add a seed crystal to this flask, and instead of dissolving, and instead of remaining undissolved, if it dissolved, it would indicate it was unsaturated. If it didn't dissolve, that would indicate I had a saturated solution. In this case, we see something different. The seed crystal starts to see additional crystal growth from it. So we see crystallization of the solute from the solution. That indicated the solution was supersaturated. Probably, and indeed it was, heated up to dissolve excess solute and then cooled slowly without mechanical disturbance to provide more solute than should have been stable in the solution. So I say the solution is supersaturated. So I added that seed crystal. So I took a little bit of the seed crystal. This was sodium acetate, was the solute. So I added a crystal of sodium acetate. I dropped it into the round bottom flask with the solution, and I noticed immediately crystal growth. Do you see the crystal growth here? There's also many YouTube videos that show this live with respect to the crystal growth, so you might want to watch some of those videos. You just search for sodium acetate crystallization from a supersaturated solution. That should give you many video options. That's a very common crystallization process. I continue to see crystal growth if I watch the round bottom flask, and then pretty soon I see so much crystal growth that you don't notice the solvent. It's actually trapped in the lattice of the crystal. And if we go ahead and turn the flask on its side, we can see that we had indeed a lot of crystallization. The excess solvent is still trapped there. We can even invert this if I have a high enough supersaturated solution that I began with, and I don't see any solution dripping out, even though the solvent's still trapped in that crystalline lattice. So very interesting process. I just had so much excess solute that when it crystallized, any ester solution that was now saturated is now just trapped within the crystal itself. It's still there. If I heated this up, it would redissolve, and I could form the supersaturated solution again and repeat this demonstration over and over and over again. So there you've seen a few different types of solutions. You should know the definition now of saturated, unsaturated, and supersaturated solutions. Now, when I look at solution concentrations, before we've talked about molarity. So when I look at molarity, remember molarity with a capital M relates to moles of solute per every liter of solution. So we did those calculations in the part 1 solution calculation tutorial. I'm going to show you a few other concentration units. I'm not going to actually use these for calculations today, but we'll see them later on in the course when we start looking at solutions in greater detail. The other types of solution concentrations we could work with are molality. Now we use a lowercase m for molality, so the capitalization really does matter here. Molality is the moles of solute in the kilograms of solvent that we're dealing with. And there's some calculations where this is quite useful because we'll find that the volumes of solution in liters can change with temperature. Whereas mass of solvent that I'm dealing with, and moles of solute, is temperature independent. So if I want to do studies of, let's say, solution properties at a variety of temperatures, I might want to use molality for my calculations. If I'm only talking about working with my solution at around room temperature in the laboratory, then molarity is very easy to work with. It's simple to weigh out the moles and measure out a volume in a volumetric flask and the number of liters that I'm interested in. Another concentration unit for solutions is part by mass. Parts by mass would be the mass of solute over the ratio of the mass of the solution. So for example, this could be the grams of solute over the grams of the solution I'm dealing with. So that'll be part by mass. We can also have parts by volume. That would be the volume of the solute over the volume of the solution. We often will use parts by mass when we have a solid that we're dissolving, but parts by volume is very useful when we have a liquid I'm dissolving in another liquid. So I could measure with a graduated cylinder the volume of the solute liquid in the volume of the entire solution. Okay, so that's really easy to do when I'm working with just liquids. I can also deal with mole fractions. Now my mole fractions will be the moles of a solute divided by the moles of every component in the solution mixture. So if there's only one solute, I just divide by the mole of that solute plus the moles of the solvent to get my mole fraction. If there's 2 or 3 or more solutes, I have to add in the denominator here the moles of every solute component. So I would add up all the solute moles plus the solvent moles, divide that into the moles of the solute I'd like to know the mole fraction of. Okay, we'll use those types of calculations when we're looking at a variety of processes. Sometimes we work with them with partial pressures and gas laws. Sometimes we work with them with other calculations as well. Okay, now that I've mentioned that, we're still going to focus on molarity now. I just wanted to introduce you to those other concentration terms. Now, when I perform a dilution of a solution, this process will produce a less concentrated solution from a more concentrated solution. This is occurring by adding more solvent to your solution. So now you have the same amount of solute, but a larger total volume for the solution. So that would result in a decreased molarity. So for example, let's say I have my concentrated solution here. I add solvent till it, let's say I double the volume. Now the number of solute particles are identical in solution, but now since I double my volume, there's half as many solute particles for the same original volume that we had looked at. So if I take half of that solution now, it has half the number of solute particles because I had doubled the volume of the solvent. Now, if I want to look at how this relates, though, I can realize the moles of the original solute is the same as the moles of the solute after the dilution process. So my moles of solute initial is the same as the moles of the solute final, but the molarity has changed. Now I can determine the moles that I have of a solute by taking molarity times the volume. So if I take the molarity that I initially had, so the moles here, I can take molarity times the volume. Whoops. I can take the molarity initially here times the volume initial. That'll give me the number of moles that I had to begin with. That's equivalent to the moles I end up with. So I can take the molarity final times the volume final. That gives me the moles that I still have. So I can set molarity initial times volume initial is equal to molarity final times volume final as an equation to calculate dilution conditions. Now, sometimes you'll see this equation written as CIVI, the initial concentration as a capital C rather than a capital M for molarity. And then you'll see the final concentration as a C sub F, V sub F. So sometimes these molarity units terms will be written with a capital C because we can work with other concentration terms. Today I'm going to use molarity, so I'm just going to use capital M's. Now, I sometimes write my initials as just 1. So you might see an M1V1 is equal to my finals as 2 rather than subscript F's as an M2V2. So if you see M1V1 equals M2V2, it's still related to these dilution processes where the 1s are the initial molarities and volumes and the 2s are the final molarities and volumes. Okay, so those are the different ways we might express this equation. Let's try applying this equation to several types of dilution calculations. First of all, let's consider that we're preparing a solution that we want to have 60 milliliters of. So I'd like 60 milliliters of this solution, and I'd like the molarity to be 0.2 molarity of nitric acid HNO3, right here. Now the stock solution I'm using to prepare this solution from was already prepared at a 4.00 molarity of nitric acid. So I needed to find out what volume of that initial stock solution I should use to prepare the final 60 milliliters of the 0.2 molarity lower concentration. So the equation that I should look at when I'm looking at changing concentrations, changing molarities, is my M1V1 equals M2V2, or initial molarity times initial volume is equal to final molarity times final volume. Now, to keep track of all of your variables in equations like this, I recommend setting up a simple table where you have initial conditions and final conditions. So I'm going to set up my table. My first column is going to be initial conditions. So M1, my variable for my molarity initial, is 4 molarity. My volume 1, my initial volume, I don't know. I'm not sure how much of the stock solution I should use in the dilution process. So that's what I'm going to solve for, is V1 here algebraically. Now my final molarity for this calculation is going to be the final molarity of 0.2 molarity of the nitric acid. My final volume, I was told I want to prepare 60 milliliters of the solution. So now that I've defined all of my variables to make sure I'm not mixing any of them up, I'm going to go ahead and solve for the unknown variable, volume 1. So to do that, I divide both sides of my equation by the molarity initial, the molarity 1. So I generate the following equation. My initial number of milliliters of nitric acid is equal to my molarity of the final solution times my volume of the final solution divided by my molarity that I had of the initial stock solution. The stock solution is just the original solution that we began with that we are now going to dilute from. So somebody prepared a stock of a higher concentration from the original nitric acid. Now my volume 1 is going to be calculated by plugging in all the variables I've already defined. So make sure you're not mixing up your variables like M1 and M2. I often will see students accidentally plug in the wrong values, but these tables will help you keep track of everything if you always prepare the table first. Yes, it takes a few more seconds, but it can often reduce your errors. Okay, so I go ahead and take the final molarity and the final volume. So 0.2 molarity times 60 milliliters. I divide by the stock solution molarity, the initial molarity of 4. That gives me a V1 of 3.0 milliliters. So that tells me I should use 3.0 milliliters of the stock nitric acid, the concentrated solution. Now, when I prepare the solution, if I were asked on a test question how to prepare the solution, I would take the 3.0 milliliters of the nitric acid, and I'm going to be diluting it in water until it reaches a total volume of 60 milliliters. Sometimes students will assume that you could just add 57 milliliters of water to the solution. I have to be very careful because oftentimes when I'm adding a more concentrated solution to water, there can be slight volume changes. So a better way to do this might be to take 30 milliliters of water, add the acid to the water. That's actually much safer because diluting acids is an exothermic process, so it can cause spattering. So I want to gradually add the acid to the water, so if it spatters, you're getting a diluted solution of acid that has more water content. So I might take 30 milliliters of water, not the full 57 you might have thought. I add 3 mils to it gradually. I swirl that to dilute the solution, and then I keep adding my solvent, my water in this case, until I reach a total volume of 60 milliliters. The ideal situation would be if I had a 60 milliliter volumetric flask. If I don't, I might have to use a less precise device. I might have to use a graduated cylinder or another piece of glassware to gradually dilute to a total volume of 60 milliliters. Now let's consider that we don't know the molarity of a solution. So we end up wanting to solve for the molarity of a solution that we're preparing by diluting 500 milliliters of a 6.0 molarity solution of a solute to 750 milliliters. So you notice that the volume of the solution is increasing. That's a hint you're dealing with a dilution process. So in this case, I would like to solve for the final molarity M2. So I'm using the same equation. What I recognize is my initial molarity is 6.0 molarity. My initial volume is the 500 milliliters of this solution. I'm going to keep adding solvent and mixing everything to make it sure it's uniformly mixed until I reach a final volume of 750 milliliters. But I don't know the final molarity yet. So there's my final volume of 750 milliliters. Now I'm careful not to say that I just add 250 milliliters of water because the volumes aren't always additive. So I keep adding water until the mixture volume is 750, and that may be a slightly different amount of water than just adding another 250 mils. Now I took the molarity final that I'd like to solve for. I isolated M sub 2 by dividing both sides by the final volume algebraically. Now, sorry, this should be N sub 2 here. My molarity final, though, would just be my initial molarity of 6 molarity times my volume of 500 milliliters divided by the final volume of 750 milliliters. So my molarity 2 is equal to 4.0 molarity. Now that makes sense. If I had doubled the volume to 1,000 milliliters or a liter, my molarity would be half this initial value. It would have been 3. Since I didn't quite double my volume, my molarity ends up with that increase in volume of 25% here. Or 50% in the original, ends up being at 4.0 molarity. Okay, so this is a reasonable answer. So you notice these are fairly simple calculations. Now let's consider that we have a concentrated solution of hydrochloric acid. Now my concentrated solution of hydrochloric acid is 12.0 molarity. So that's my stock solution that I'm using, that I'm beginning to prepare my dilutions from. I would like to prepare 8 times 10 to the second, or 800 milliliters of a dilute solution of hydrochloric acid. That would be 0.120 molarity. Now, if you notice that this molarity is 100th the stock solution molarity, that's going to help you predict how much of the original stock solution you're going to use. But let's go ahead and confirm this. So I'm using the same equation. I set up my table of defined variables. My initial molarity for the stock solution of hydrochloric acid is 12 molarity. My volume initial is unknown. That's what I'd like to solve for. My final molarity is 0.120 molarity. And my final volume that I'm diluting everything to is 800 milliliters. So how much of the original stock solution should I use in order to achieve preparing this diluted solution? So I'm going to go ahead and solve for volume 1. I take the molarity final, M sub 2, is a 0.120 molarity. The final volume is the larger of the two volumes in this case during the dilution, so that's 800 milliliters. My stock solution molarity, my initial molarity, is 12.0 molarity. So my molarities will cancel. I end up with milliliters for my volume. And I see that I have 8 milliliters of the stock solution that I should use, and I'm going to be diluting this to a total solution volume of 800 milliliters. Now this is a very concentrated acid, so it would be better to take several hundred milliliters of water and very slowly add the concentrated acid to the water because of the exothermic dilution process that would release heat. We don't want to cause the concentrated acid, to boil and spatter, so I wouldn't want to add water to it. Instead, I add it solid water, so if I cause any spattering, it's mostly water that I'm spattering or a very dilute acidic solution. So I go ahead then and add the 8 milliliters of the hydrochloric acid to several hundred milliliters of water. Then I keep diluting it with more water and mixing till I get a total volume of 800 milliliters. So that's how I would actually perform this dilution in the lab. I often have been known to ask students to describe how to prepare a solution in the laboratory other than just giving me this final answer. So I'll see if they understand how to prep the solution. Okay, let's do one more calculation here in this tutorial. Let's consider how to look at the concentration of an ionic compound and the concentration of all the ions in that compound in that solution as we're diluting the solution down. So I'm just going to start with a 0.127 molarity solution of a solute. My solute is calcium nitrate. And I'm starting with a 20 milliliter sample of this molarity of solution. I'm going to dilute that down to a total volume of 5 liters. Now notice my volumes are in different units, so I'm going to have to convert one of these two units to the same unit. Perhaps I'll convert the milliliters to liters. Okay, so again, this is a dilution process. I started with 20 milliliters. I'm diluting it up to a volume 2 of 5 liters. So I went ahead and defined my variables. My initial molarity was the 0.127 molarity of the calcium nitrate. The initial volume is 20 milliliters. The final molarity is what I'd like to find out. What is my final molarity once I dilute this initial 20 milliliters to a total volume of 5 liters? Now I'm going to go ahead and divide my 20 milliliters by 1,000 to convert it to the number of liters that I have. I would like the same unit for both of my volume terms. So if I want to solve for my final molarity, I just divided both sides of my dilution equation by the final volume. So I take the molarity initial times the volume initial divided by the volume final for the diluted solution. So I take 0.127 molarity times the 0.0200 liters. Notice I converted the 20 milliliters to liters. And I divide by the final volume of 5 liters, so I notice now liters will cancel. If you always write your units down, you would catch if you had forgotten to convert these to the same units. Now if I converted the 5 liters to milliliters, the milliliter to milliliter ratio would have also given me the same answer. So I could have done either conversion and ended up with the correct answer. So if I go ahead and solve for the final molarity for this solution, I end up with a molarity of 5.08 times 10 to the negative 4th molarity of calcium nitrate. It's such a low concentration because my concentration was somewhat low to begin with, and I diluted to a fairly large volume of 5 liters when I only had 20 milliliters to begin with. So I'm really not surprised that I have such a small molarity here with the dilution. Now that's the molarity of the formula units in the solution of calcium nitrate. However, calcium nitrate doesn't stay in solution as individual formula units. It's a soluble ionic compound which goes through a process we call dissociation, where the ions end up separating and being surrounded by water molecules. So if I'd like to look at the molarity of the nitrate ion, the resulting diluted solution, it's actually going to be a different molarity than the molarity we just calculated. We calculated that calcium nitrate was 5.08 times 10 to the negative 4th molarity. However, let's consider what this ionic compound formula does in water. The compound dissociates, the calcium nitrate dissociates, and for every formula unit we end up with a calcium cation, since there's one calcium cation in the formula surrounded by water molecules, and since there's 2 anions in every formula that had been balancing charge, we end up for every formula unit producing 2 nitrate ions. So I want you to notice we have twice the number of nitrate ions as the original formula unit, or twice the number of nitrate ions as the number of metal calcium cations in solution. So if I calculated that the formula concentration solution was 5.08 times 10 to the negative fourth molarity of calcium nitrate, when I think about the anions that have dissolved, it's twice the molarity. There's twice the number of particles than the original number of formula units we began with. So I take that molarity we had calculated for calcium nitrate and multiply by 2. So I end up with 1.02 times 10 to the negative third molarity of nitrate ions. It's just twice the original formula molarity because there's 2 of those anions in every formula unit. So I end up with double the number of ions of that type compared to the original number of formula units. Now what if I ask you this next question? What is the molarity of all the ions in that solution? Now that would include all cations and all anions. Now luckily there's only one solute. If I had multiple solutes, I might have to add up the molarities of every single ion from every single solute. But I could do that. It just requires a little bit more work and a little bit more careful bookkeeping that you're adding up everything and you had calculated everything originally for its molarity correctly. So here, though, I'm just looking at the calcium nitrate. Now, I need to recognize every formula unit of the calcium nitrate produces 3 ions. What I mean by that is it produces 1 metal cation for each formula unit and 2 nitrate anions. So since I just said all types of ions here, of all ions in solution, we can add up the molarity of the metal cations and add up the molarity of the nitrate ions. Now, since I know that I had 5.08 times 10 to the negative fourth molarity of the calcium nitrate formula, I end up with the same molarity of the calcium ions because there's a 1-to-1 ratio here in the relationship. 1 calcium cation in the formula gives me 1 calcium cation in solution. So I have the same molarity of metal cations. However, since 1 of the moles of the calcium nitrate formula units gives me 2 nitrate ions, I had to double the molarity there just like we did on the previous slide we looked at. So if I add up the molarity of the calcium ions plus the molarity of the nitrate ions, so that was twice this 5.08 times 10 to the negative fourth. If I add those 2 up, I get 3 times the original formula concentration because I end up with 3 ions for every formula unit. So I end up with 1.53 times 10 to the negative third molarity of all of the ions present, all cations and all anions. Now, you might ask yourself, why do I care about the molarity of the ions in solution? Well, there are a number of properties that we call colligative properties that can help us predict the physical properties of solutions based on how many particles you have dissolved in that solution. And these are generally, we can ignore the identity of the particles. So it doesn't matter whether I have cations or anions or neutral molecules, just however many particles I have dissolved in a solution will affect physical properties like boiling points, melting points, vapor pressure, those types of properties due to the number of solute particles. So in that case, I would want to be able to calculate the concentration of all the ions in solution. Now, many times for those calculations, we might use units of molality, but here's a nice bit of practice for relating it to the concentration of all ions via molarity. Now, this is our last example calculation in the tutorial, but I will have a review sheet that I will give you that will have a number of additional solution calculations and dilution calculations that you should practice to be ready for the next exam. Okay, thank you very much. I hope you have a great day.